Hi there, I'm Robin, and this presentation is on the verification of hardware. So, as most of you probably know already, it's difficult to write hardware that behaves according to its specification. What's more so, it's difficult to guarantee that your implementation really is correct. Existing tools either require a considerable amount of expertise or fail to provide full proofs as a guarantee. We propose to use refinement typing for verification to find this nice middle ground where we provide proofs but also have some automation to relieve the burden of proof theory for programmers. Refinement types is a software verification technique that's used to primarily do stuff like bounce checking on array indexes or totality checks on functions. It's an automated theorem proving technique such that users need to only write small annotations on functions, if any at all, for interesting properties to be checked for their system. The annotations are just restriction of type to a subdomain. Consider the following refinements. For example, the natural numbers, where we take the integers as a base type and then restrict it via the predicate v is larger or equal to 0. Any member of this type now satisfies the predicate, and the remaining integers that do not satisfy it are also no member of the natural numbers. We can create many more subdomains, and two other examples are the non-zero type, where we exclude 0 from the integer domain, or all even numbers. So what do we achieve with these refinements? Well, we can use them as pre or post conditions into a function. For example, the division of two numbers requires the denominator to be non-zero, because otherwise the program would crash. As such, we place it as a precondition into this function, such that a caller of this function has to prove the input cannot be 0. Conversely, we can place it as a post condition. For the absolute function, we know that the output should be a natural number, and we refine it as such. Any caller can use this property inside of its proof, if applicable. In the first example, we divide 10 by 2, and clearly 2 is not equal to 0, so the system is easily validated. In the second example, though, the denominator is provided by the absolute value of any number x. Since the natural numbers include 0, we have no proof to show that the denominator cannot be 0, and as such, this function is rightfully rejected. But now that we have a general overview of refinement typing, how do we apply it to hardware? Well, admittedly, there is some great overlap between refinement types and functional HDLs, and as such we'll be using a functional HDL for the rest of this talk. But even so, the properties we wish to prove are very different. In software it's common to do bounce checks or totality checks, but in hardware this is rarely the case. So the specification that we prove is very different, as well as how we prove it, as hardware's execution model is significantly different from that of software. Commonly in hardware, we make operations that last multiple cycles, but in actuality we do this only for optimization of size and speed of a system. But in reality, for correctness of the system, this isn't required at all. And as such, any specification of a system should just contain the operations and the full transitions they do. And this specification is thus also super similar to reading a reference document of, say, an instruction set, where we can read this instruction affects these registers or these memory addresses, or affects these flags, and might behave differently depending on the status register that is in the core. But now we need to capture such a specification inside of the refinement language, and we do this as following. Here we have a toy example with two registers x and y, where the next state into the system, a transition from the system, goes to x prime and y prime. Well, in this toy example, the x prime and y prime are simply an increment of their prior state. Given a specification in the refinement language, we still need to show that the implementation we build is actually equivalent to the specification. Now, our implementation will still contain multiple cycles for optimization, and as such, to show equivalence, we need to capture parts of the whole transition over multiple cycles. So in this way, we accumulate the whole transition over these multiple cycles. We accumulate it via invariance over the circuit, but then why invariance? So consider this schematic of a sequential piece of logic. In this combinational logic, if we wish to show any adherence to the specification, then we very likely have to use some refinement on the state, on this input state of this combinational logic. And clearly, since this input state is provided by the same combinational logic at a previous cycle, the refinements that are provided as the input state have to be provided as the output state as well. So if you consider the type signature of this combinational block, you'll have to see that the S's, or the state, both get the exact same refinement, and in turn they have an invariant over them. How do we actually use these invariants to show equivalence to our specification though? Well, first of all, take this base implementation for our specification, where a toy specification, where we increment x and then y at two different cycles, which together makes up a full transition. Now, we try to synchronize our transition in this system with a full transition in the specification. As such, we've placed a maybe specification as the output, where if we increment x, well, we do not synchronize yet, as we haven't incremented y. In the next cycle, we increment y, and as such have done a full transition step. So we output just with our specification. Now, as it is now, we cannot actually show that our specification is correct. It knows that y prime is in fact y plus 1, but there's no guarantee that x prime is in fact x plus 1. So we solve this by placing a refinement on the state. With the following refinement, we'll know that when we enter the second cycle, where we synchronize with our specification, that x prime is x plus 1. Now all the other cycles also have to guarantee, and in this case the cycle before it has to guarantee that x prime is in fact x plus 1, which it does. And as such, the specification is now correctly validated. With this method, we were able to specify an instruction set architecture for which we could verify that our implementation of this was in fact equivalent. So it's basically modeled after the RISC-V architecture, but due to small incompatibilities with the HDL we used and the refinement type system, we couldn't actually make the RISC-V architecture. But in a theoretical point of view though, it's exactly the same thing. And the properties we were able to specify ranged for changes of the register file based on the instruction that was executed, the program counter, the instruction register, of course commits which operation is done, but then also the addresses of memory reads and writes, as well as the values that are written to memory could be verified. We've also been working on the instruction ordering of processors to show that they retain causality when they retire instructions out of order. We use some complex pairwise and bounded refinements to achieve this, which are an advanced feature of the refinement type system. Apart from this, we believe that greater inference is possible, and we'll be working on this as well, to alleviate the program of writing these small annotations even more.